So Thomas will tell us about something completely different, the Chern-Simons theory and relations to Humphrey point.
Yes, thanks. So, yeah, preparing this talk, I realized how little I understand about all this Chern-Simons theory business and how much there is surrounding it. So if the picture is not complete, I'm sorry about that, but I'll try to make it as complete as possible. But that's difficult in 50 minutes, so let's see. So I'm going to start a little bit sort of on the math side. So a math TQFT, what does that mean? What is it that we talk about when we say TQFT in math? Well, there's several ways of formulating this, but I'm going to do the sort of slightly categorical version because it's nice for chopping up pieces. So I'm going to talk about cobordism categories.
Do you want to try a different marker? I don't know.
Yeah, okay.
I don't know.
Yeah. Better. So, what is a cobordism category? Well, it's sort of, you have objects are just, let's say D plus 1. Objects are D manifolds, but now I'm going to say with structure, because we're going to need structures here. Morphisms, what are those? Well, they're cobordisms. D plus 1 dimensional. And what kind of structures do we put on them? Well, I mean, you don't have to have any structures. This could just be the cobordism category of d-dimensional manifolds. So, oh yeah, I should say something about composition. So let's call these sigma and these m. So if I have sigma at one end, then of course composition is a sigma 1, sigma 2. Oops. And then you have sigma 2, and this is m. And you have m sigma 2 to sigma 3, so now sigma 2 is the same thing. It might map to to this. So somehow you want to say that there is a boundary minus. Oops, this is m1, this is m2. There's a boundary minus of m, which is sigma 1, and there's a boundary plus of m, which is sigma 2. So you have a source and a target boundary. And this is how you compose. You just glue to equals composition. You glue over sigma 2 of these things. So that's the sort of cobordism, the idea of a cobordism category. And now what kind of structures do we want to put on? The most important we're going to talk about today is framings. So I'm just going to define exactly what that one is and maybe say a little bit about other structures, but sort of framings. And there are actually two types of framings here that I'm not gonna, well, there's three things if you ask as about topologists, I think. But at this point, a framing just means that on cobordisms, you have a trivialization of the tangent bundle. But requiring that at boundary minus m, the d plus first vector here in Rd, you have sigma boundary minus of m. You have that this trivialization of the tangent bundle is supposed to set this incoming vector into the manifold is supposed to be sent, let's call this v. Then v goes to 0, 0 up to 1. So it's supposed to be basically it's supposed to be a trivialization of the tangent bundle of the boundary plus an extra incoming vector. And at the positive end or the out,
v goes to that vector under what map?
This is the tangent vector, and Tm goes. At the other end, it's the other way around. It's the out vector pointing out, which is why you get opposite orientations if you're doing just orientations and not framings on the other end of a cobordism, because it has to point out. So yeah, these in this way they compose very nicely. You might want to say something about colors, that the trivialization is very trivial in a neighborhood or something, so that you can just put things next to each other and get actually smooth trivializations over this thing. But that's technicalities, and you can always sort of use a color neighborhood to set this up. So this is the cobordism category, and then the question is, what is a TQFT? Well, here you have an operation called direct sum. So it's formally it's a strict monoidal functor. Let's call it C, from cobordism with some structure. And now I'm just sort of generally, you want to put in any structure. In this talk, it will be framings for the Chern-Simons theory. But in general, it's just some structure, some d-dimensional cobordism theory, d plus 1, with disjoint union as the monoidal, meaning that you have an operation on this category that's very categorical. It's just disjoint union. And this is supposed to be a functor into Hilbert spaces with tensor product, which is the monoidal structure we're using on Hilbert spaces.
Sorry, what is the upper decoration of cob? Cob upper what?
Structure.
Structure, okay.
Just means some decoration.
Okay.
Actually, I wouldn't want to call it decorations because we're getting to that later. This is sort of like structure on the tangent bundle level.
Yeah.
You could also talk about decorating the surfaces or whatever we're looking at, and that's what I'm going to do. So, okay. So it's a function like this, but it has to satisfy some axioms, such that. And now because I got a little confused of what axioms are needed in this formulation as compared to the other versions. So I'm just going to put all axioms and formal properties that comes out of it. I'm not sure exactly which points are needed, but they satisfy all of these at least. Yeah.
It's infinite dimensional, finite dimensional.
Yeah, right. Good question. So you can do infinite, you can do finite, you can do whatever. So if you do finite, we would maybe just say inner product complex vector spaces in math. But since physicists don't really care too much, they just say Hilbert spaces. And in fact, the Chern-Simons theory is going to be finite dimensional. So if you want to, you can just think of that.
Yeah, because otherwise it's a bit ambiguous to say tensor product. I mean, you have different.
Yeah, right. That's part of the issue. So this is finite dimensional. Let's stay there. But yeah. Okay. So yeah, what does it satisfy? I have a long list. That's kind of important. So yeah, if you take C of some sigma, it's going to be isomorphic to C of sigma prime if sigma is isomorphic to sigma prime. And when I say isomorphic here, I mean with whatever structure we've put on. So if this is framed, then this is a framed diffeomorphism preserving the framings. And this is functorial, kind of going to be important. And now I'm also going to sort of hand wave a little bit because functorial here, I mean, I defined morphisms to be cobordisms here. Now I'm also talking about a different type of morphisms of the objects. So in some sense this is something like a two category or something, but I'm just saying that if you look at the space of objects and look at the diffeomorphisms that preserves the structure, this is supposed to induce isomorphisms functorially on that level. So you don't have to think much more than that. You don't have to set up a big structure. So what about on the level of cobordism? Well, it's the same thing. Oh, yeah. I should point this out, that it means that sigma goes to Hilbert space, sigma, and cobordism goes to maps from the minus boundary Hilbert space to the plus boundary Hilbert space. That's what it means to be a functor from this cobordism category, right? You just associate a Hilbert space at one end and the other, and you have a map. Maybe you want to put a bracket here.
Continuous linear? Or?
What?
You mean linear map?
Yeah, linear. Hilbert space is
bounded linear operator.
Yeah, but finite dimensional.
Yeah,
so
finite
linear
dimensional.
map.
Okay.
Yeah. So that's sort of the first thing. Then the second thing, I have on my list is just a dual thing, that if you take the opposite structure on sigma, which in this case means that you just flip this v in the other direction, then this is supposed to be the dual vector space. Which is one reason to say Hilbert if you're infinite dimension, because then this actually makes perfect sense. Okay.
So sigma bar means sigma with opposite orientation.
Well, if it were oriented cobordism, if it's just orientations you're putting on your ends, then it would be opposite orientation. But here it's the framing where you flip the. Yeah. So here you had this V pointing in. Now you want the framing such that when you make the V point out, it's sort of here. That might be a little.
Yeah, it's
Yeah, but I mean. Yeah, but yeah. Okay, say flip orientation here, but it's it's the opposite framing you're really supposed to put in there. But yeah. So. Okay, so what other formal properties? Well, the monoidal, strict monoidal part I just wanted to write out because if you don't know what this means, it's just saying that if I take this term union, this is going to be the tensor product. And if you do it for cobordism, it's the tensor product map. So I'm just not going to write that down. Then this was maybe 3, I don't know, 4. If you take the empty d-dimensional manifold, you're supposed to get your ground ring, so I'm going to call that lambda. This is, for this sake, just restrict to R, integers or complex numbers. And same for cobordism. If you take the d plus 1 empty manifold, which is a cobordism from the empty manifold to the empty manifold, this is supposed to be the unit, so we at least want a unital ring. But since we also want to dualize and stuff, we want other structures as well, all of which we have here. But in general, you might want to think exactly what kind of structure you want to put on the ring to get this kind of.
Sorry, cobordism is supposed to give us a map?
Yeah.
And
from C to C.
So a map from this to this is a multiplication by something.
Okay.
And I'm saying it's supposed to be 1 for the empty
okay,
thing. Okay. And the dualization action, maybe I should just put that on here. If I take Cm in, yeah, this is over here. So, I'm going to put it just next to it. So this dualization axiom is basically saying something around the sort of following thing. If I take some sort of cobordism, I can actually think of something that's an output as moving it to an input. So I sort of want to think of this as being equivalent to doing this. So if this is sigma 1, this is sigma 2, I want to do sigma 1 here, sigma 2 opposite here. And sort of combining this dualization axiom with some of the others and stuff, you get this sort of different variation of defining what a TQFT is. Where you, instead of saying it's a cobordism category thing, you're saying that it's just something that takes M manifold, D plus 1 dimensional manifolds and associates a Hilbert space to boundaries. I think of everything as incoming. I mean, yeah, I'm basically saying we think of everything as incoming. And then always just consider maps to the empty thing. But then if you do this, then you have to really care about this axiom here a lot. Because then the composition is this pairing you have to do. Because then if you take something like this and also think of it as something like this, empty to sigma 1 bar and sigma 2 bar. Oh, not bar anymore. Now you can sort of compose these two and get just something in the ground ring. So in general, you see that if M is closed, sort of what's 5 here, 5 is saying that if Cm is a vector in the boundary of Cm. This is interpreted like this, that a linear map, this is, so C of this gets a linear map into this Hilbert space tensor, sigma 1 tensor H sigma 2, sigma 1 bar. We have a linear map from this. This is the point of dualizing. We could put this on the other side, flip this over and do usual things. But now you think of this as a vector because you can see where one lands. So you think of this associating a vector to the boundary instead of maybe morphisms between two parts of the boundary. And so this says that if I take any manifold where this is in maybe the minus boundary, I don't know, where M has sort of no positive boundary, then when you look at M bar, this is supposed to be a vector inside the positive boundary, which is now the same as this but opposite. So I should a dual. So this makes the statement that if you just take bar, you get a vector in the dual boundary, and now you can think of composing this with this as just the pairing in the dual stuff. So there's these two viewpoints, whether or not you just work with one boundary and fillings and write out all these formal properties, then you don't need all of them. Then there's this other viewpoint as a functor, and then you write down some of the other of these properties, and then the rest follows. I'm sort of not sure which one is needed in which case precisely, but since you can just put in all of them, I'm doing that. Yeah.
How do you, I don't understand how you transform an outgoing vector into an ingoing vector when you do the trick of doing sigma 1, sigma 2 bar, because you just reverse the orientation of the boundary, not the fact that the vector
You
is...
did.
I don't...
So, yeah.
Well,
I don't... Yeah.
just
I
here you
think
have
when your category is with these framings,
Yeah.
then the bar is not the orientation reversal, it's some operation on the framings, right?
yes, yes.
So you have to kind of figure out what that is, in a sense.
Yeah, but
What is a bar operation?
what is the
Well,
bar?
on the cobordism or...
Yes, on the cobalt.
Oh,
Because you have...
Then you...
oh, but that's just shifting what you view as minus or plus. It's the exact same structure. You're just shifting what part of you view of minus boundary, what else you view as plus boundary, which means you're sort of getting the opposite induced framings on the boundary. I should probably,
Okay.
yeah. I mean, it's sort of a canonical map to take a framing and then flip one of the vectors. And this is homotopic to flipping any of the other vectors, at least stably. So you want to say something like if maybe you flip one of the others when you do it in the boundary and then you rotate around a little bit. But you can, yeah.
So what you're saying is that if M has no boundary, then the bar doesn't do anything, for instance.
Well,
Should still flip the bar.
well, that's not entirely accurate.
Shouldn't it flip the bar?
It's turning it upside down.
Yeah, but from empty to empty.
Yeah. So
It's still
I missed that actually.
I don't know if this is
No. The operation on cobordism, sorry. You do flip this vector.
Yeah.
You just flip the vector, the last vector, everywhere.
Yeah.
Because then the outgoing becomes the incoming and vice versa. It satisfies the right condition with the same framings to be instead be outgoing instead of incoming and vice versa. So that's just what you do. You just flip that on the cobordism. Sorry, yes. And that also means flipping the orientation if you only care about the orientation class, not the framing class. Yes. Okay, so, yeah. Sorry. So, what about... So, the reason why one might want to do this, I haven't said much about that, is that maybe this Cm, where a boundary of M is empty, which gives you some sort of number in your ground ring, is some sort of manifold invariant, and you want to compute it. So you can cut up and compute maps along the way. You can sort of take some sort of very complicated D+1 manifold cut it up along the way, and then look at Hilbert spaces of the empty set, mapping into Hilbert spaces of this sigma 1, sigma 2, and then map back to the empty set, H of the empty set, which is just the ground field, or ground ring. And now the composition of these are of course going to give you this invariant. And so if you know what happens whenever something simple happens, like for example attaching a handle or something like that, you can compute this thing by computing it piece for piece and then compose it. Of course, the payoff here is that numbers sounds easier, but now you have to construct some vector spaces, and you have to satisfy all these axioms, and that's the point of Chern-Simons theory and Wittens and some other paper by Seiberg and who was it you said? Dragomir. That proves that Chern-Simons theory satisfies these axioms for the framed structure. Okay, so let's shift to Chern-Simons theory. So I don't have time, and I don't fully understand it, how to give a complete mathematical definition of Chern-Simons theory. So I'm starting with the physicsy hand-wavy business. So what is Chern-Simons theory? Well, you want to take your manifold, so D is equal to 2 now. And you take your manifold M, so first case, M3, where boundary M is empty. How are you supposed to write down some number, complex number in this case? Oh yeah, let's put out that. How are you supposed to write down some number associated to this manifold? Well, the physics definition is something like this, or also math, but almost math. I mean, yeah. I don't know. So you look at, take vector bundle, take principal, oh yeah, you have a group also. Principal G bundle, group G, which is a Lie group. Take principal G bundle, E over M, look at all connection.
So principle is not spared in the graphic way.
It's okay.
Like this?
Yes.
Ah, I should change that into a few papers then. Okay.
Which principle?
I'm getting back to that. This was something that confused me. It's confused me several times, and then I thought I've resolved it, but now I think I have. I was talking to Jan about this morning, and he was absolutely right, and now I understand why, I think. So you look at all connections on this, and let's call them A. So some connection A. Then you define a functional, or a function, on these connections, which is defined by, you take M and integrate, I might want these factors in here. K divided by 4 pi, so K is some natural number, or maybe an integer. I don't know. Yeah, okay. So then you take A wedge dA plus 2/3 A wedge A. So here you're using a lot of structure. You have a Lie group. You have a Lie group G, which means it has an associated Lie algebra. To define a connection, you need a one form on the principal bundle taking values in this Lie algebra, which satisfies some invariant conditions. And when you wedge forms like that, they're officially going to take values in the tensor product of the Lie algebra with itself. But then because it's a Lie algebra, you can use the bracket to contract. So these are all going to be valued in the Lie algebra, but then I'm going to put in a TR for trace. Maybe I only want to, You take the trace of this, so you're basically contracting everything, and you get some number that you're integrating.
So with respect to the killing or whatever.
Yeah.
Yes, there's one invariant up to scale, so naturally,
Yeah.
if it's semi-simple or whatever.
Yeah.
Okay.
Yeah, so since we're not going to need much of this
Yeah,
detail, I didn't look it up completely, but it's like this. Now the physics definition of this thing is we take this partition function of M. It's going to be you integrate over the space of all connections, and this is why it's physics at this point. And then you take this e to the I SA, and then you do something with a measure on the space of connection, again why it's physics, because it's provable that this does not actually exist in satisfying the formal properties you want it to exist. But then physicists answer back by saying, well, we want this to satisfy some formal property, not this. So let's just look at the formal properties that an integration is supposed to satisfy and do that. And that's sort of the short version. Yeah.
Sorry, this Z is not the same as that Z, right?
It is.
It is.
It's a
But
number.
this is an element, and this is
Close man.
This is a closed
Ah,
manifold with no
right.
boundary, so it's supposed to just be a number.
okay. Thanks.
And this gives you the number, depending on K and your Lie group.
So
Yeah.
again, it's important to frame what is insurance.
Yes. Framed, so I mean cup framed too. That's the category we're in here. And I have to admit I did not understand the argument why the framing was so important in what I wrote. I was reading Witten's paper on this because it's very nice, but his argument is something like when you try to regularize this, you get something that looks like a quantum gravity operator or something, and you should know.
Well, there's an anomaly
Yeah.
if you don't do that.
Yeah, there's some anomaly coming from the trivial representation, and if you just compensate for that using a framing, then you're happy. But, I mean, that didn't make me very happy. So. But, yeah. Okay. I mean, there are mathematical way of interpreting this and writing it down, and that's also what was done in this early paper. Written also writes again in the paper I was looking at this point. So, what about when M has boundary?
Sorry, so the theory depends on G and on K,
Yes,
and you were going to say something about E?
E.
Which bundle?
The bundle?
Oh, yes. Let me do that first. Yes. Which bundle? And the answer is all. And the reason for this, I can give a topological reason for that I now like. So, what is the Gates group? So, yeah, I should say that the Gates group, this is invariant under action of Gates group. This is one of the most important points. So, I should write that out. Which is a map from M into G. This is a group, and you act by it on this, and you're doing sort of equivariant integration instead of just integrating this. So it's an equivariant integration that you're making sense of in formal ways for this. So, but there's another interpretation of this that I like a lot, because what are you actually doing? You're taking a function on a contractible space. If you fix E, this is a contractible space, this space of connections. There's no choice, you can do whatever you want, it's contractible. So you have this Gates group, which is sort of script G, acting on a contractible space. And it's almost free, so let me pretend it's free. So you have this sort of contractible space, let's call it E, which, no, let's call it EG. It's a contractible space on which the Gates group acts. Now you're modding out by the Gates group. This is, if you're a topologist, it's going to tell you this is a model for BG. The question is, what is B of the Gates group? Well, I claim the following. If I take B of mapping space of M into G, this is almost, but not exactly, maps from M into BG. What's the problem with this identification? Well, formally it's just some sort of recognizing that there's some adjoint stuff going on. You just move, not adjoint even, you're just moving in. This is something you can do topologically, but what's missing here? The point is if you take B of a group, you're going to get something connected. Right. But maps of M into Bj is not connected. In fact, pi 0 of this space is isomorphism classes of bundles, G bundles.
Do you assume that G is connected from the beginning?
Yeah, okay. G is connected.
Yeah.
Thanks.
I mean, you really only. Oh, yeah, never mind.
Yeah. So if pi 0 is isomorphism classes of G bundles, and this is really the space you want, it turns out it's not this space you want, it's this space you want as your configuration space to do all of the physics, then you should add in all these components. How do you do that? You pick one vector bundle in each class and do this for each of them, and then think of what happens, describing each of the components of this space. So it's really because this is the interesting space to do the theory on, that you have to do all vector bundles. Okay.
But there's one, well, the fact that the gauge group consists of mappings from N into G, it's obvious for a trivial bundle, but for others it's not.
Oh, yeah, okay, I should. This is actually a section of so when you have a bundle E over M, this is something that people often don't write, but you're right, there is a little bit of technicality. The gauge group of E is not just maps into G. It's actually sections in fiber-wise isomorphisms of E as a bundle over M. What's it called? The adjoint bundle or something? I don't know, maybe I should say at E. It's sections like this. That's true. And so that's sort of a twisting going on, but I mean, all of the components of this thing are going to be isomorphic, a homotopy equivalent, I think. So you can model, and this is why people often restrict to the trivial case, because you look at that component. I think maybe that's not true. That's a good question. There's a lot of things, as I said, I don't fully understand about all of this, but it might be that they actually have slightly different contributions, but yeah, I don't know. Okay.
So you do this integral for every isomorphism class,
Of bundles.
and then you add up all these infinite integrals?
Well, Jan? Good, okay.
What was your response?
He was, yes.
Oh.
Okay, so
Just
I'm-
some effect to converge.
So I should go faster now. So let's talk about boundary first, quickly. So if M is not empty, boundary M is not empty, what do you do? Well, this is supposed, so let me just say a little bit, how do you actually do this then? You want to integrate this, but what does it mean? Well, the thing is, and this is what often happens in physics, you want some formal properties out of this. So you want to write it in a way where you can actually interpret it as some kind of integral of something. How do you do that? Well, you can do that by using what's known as stationary phase, because as k tends to infinity, this is going to be a very oscillatory integral. So there's a lot of cancellation, and this is sort of an informal argument. So what you say is that, what happens is that as k goes to infinity, you really get, I mean, you should think of this as a function of k now, but now if it's analytic, you can just see what happens as k goes to infinity and what happens to how the function looks at infinity. And at infinity, you can write this as some sort of contribution from flat connections. So maybe I should do that. C of m is some sort of contribution, sum over contribution from flat connections. Maybe this helps with the sum over all isomorphism classes, because maybe there are not that many flat connections in some of the isomorphism classes. I don't know. But okay.
But this this is only in the asymptotic when k goes to infinity?
Yes, and this confuses me a lot. This is asymptotic, but in some sense, if you take this sequence of numbers and encode them in this, you recover them completely. It's not just some sort of... Sometimes stationary phase is an approximation that gives you some sort of approximation around infinity of whatever's going on, but in this case it's actually giving you the invariance, and I don't fully understand why. Maybe Jan can say a little bit, I don't know. Okay. So, but it is really encoding all of these things. But you want to think of it as contributions from these flat connections that are. Oh, yeah, that's because it's the critical point. So I should say that. Not d of s equals 0 implies a is flat, or if and only if a is flat. That's the point of this thing. So. That's why you get contributions from critical points only, but you also get contribution of how the function looks close to the critical points. You get from Hessians. So in stationary phase, there is contributions to integrals, the Hessians of the integral around the point. Well, the local, not just the Hessian, the local germ around the point. But in this case, this is like quadratic and third order. So it's, I mean, the behavior close to critical points is somewhat understood, right? It's a quadratic term and there's a third order term, and that means you can do some sort of Feynman sum, and you can interpret all of this using some law that only uses trivalent graphs because there's only third order terms. But that's all technical, and I'm not going to do that. It's just sort of giving you an idea of what this thing is. But it has contributions from flat connections. So what's the math way of trying to define something like this? Yeah.
If the boundary of M is not empty, then this is not a number anymore. So how
yeah, that's what I'm going to say.
Okay.
I'm going to say. I mean, I have just boundary M not empty. So,
but before you move to this case, this fact that this is not on asymptotically, but exactly the thing. Does this have anything to do with what is called Dusterman happening without something like that?
Maybe. Tobias? Oh, okay. Sorry.
But that's precisely how you prove.
So it is.
Yeah, that's precisely what it is.
Okay, maybe I want to ask you.
Physicists say yes.
Okay. Okay. So, if you want to, now when boundary is not empty, what are you supposed to do? You're supposed to look at some three manifold that has some sort of sigma boundary. And let's just do maybe, I don't know, positive one end boundary, there's nothing in the input. Now, if you're supposed to get contributions from all flat connections, what are you supposed to put at the boundary here? Well, you're supposed to put something that when you do this pairing of inside, when you put something else on the other side and you pair, you're supposed to get this integration over all, or the sum over all flat connections. This means you're supposed to put, well, restrictions of your flat connections to these ends. Which means what you put is something like, and this is wrong, Hilbert space of flat connections on sigma. Because now you can say, well, what's the vector you get in M inside this, well, dual, maybe. I don't know. What's the vector you get inside the space? Well, that is you sort of restrict to the flat connection that has this boundary condition, and then you do this integration. That gives you a number, so you get a number for each boundary condition. But this is not how it's actually working, because you need flat connections is not a Hilbert space. That's one thing. I mean, it's yeah, and other issues. But I mean, what you technically do is very complicated. So maybe in the interest of getting to Humphrey polynomials, I'm not going to do that. What we technically do is look at holomorphic sections in some vector bundle associated to this. But then you have to put a Riemannian structure on the surface, so it becomes depending on that. But then you argue that you can remove this dependence by choosing a projective flat, so-called Hitching connection, on the bundle of these holomorphic sections. That's the short story. That gives you a Hilbert space, and then the pairing is as sort of the idea of what I said, as integrating on you're integrating on both sides, and now you're pairing to get this number. Yes. Okay. That was boundary. So what's a Wilson loop? I should say that at some point. Well, for a physicist, this is sort of, if you fix your manifold M, then this Cm is the partition function for, I don't know, observables related to M or something. Wilson loops is, in physics language, observables. But I don't think that's how I think of them. I think there's another way, but I'm not sure that's correct, but at least it's close. So Wilson loop, what is it? You look at a link inside M. And to each component, associate a representation of the group G. I don't know, GLNC here. I don't know if it's actually U, N, or GLNC, or what you do in practice here. But yeah, not so important. You have a representation. And now you realize that this integration, which I just erased, generalized, and this is how you, the physics interpretation is that if you have something like an integration and that giving you the partition function, then you're supposed to put in basically functions or operators if you're doing quantum stuff, and integrate that same thing but with this thing inside of it. So I need to define some sort of function or operator on the space of connections from this data, because I want this to be observable. What is that? It's the following thing. So any connection, so any A on this bundle E over M has holonomy around any link component. Now, this holonomy depends on where you fix your base point on this link. So you can't really, but you can define it up to conjugation, and that's good enough because we're going to say that the operator associated to this link component, I don't know what the language, maybe WLI, I think is supposed to be the trace of the representation of the holonomy using A around Li. So you have holonomy around this thing, you take a representation, you take trace, and because you're taking trace, it doesn't matter where you put the base point.
So on the left, like there's an A as an input to this function, to this.
Yeah. It's a function on the space of connection. And now you say that, well, then you define Wilson evaluation function on each of these guys. So for a component, it's just the product of these things. I don't know, L components.
Sorry, when you say around, you mean meridian?
No. And this is something that's confusing me a lot. It's around the loop itself.
Okay.
And this is very confusing to me because it means that you have to, when you do the surface part, the boundary part, you have to do something that I don't fully understand on the boundaries when you have marked points. But I'm getting to that. Well, I hope I'm getting to that. So now you have some sort of what physicists would call, well, you can take a partition, a functional associated to this is just you integrate over A. You now take your Wilson thing and plug in and do the same thing. This is called not the expectation value, because to get the expectation value you have to divide by the standard partition function, but this is the unnormalized expectation value, I think I could call it, right? Of this operator on these things. So this is giving you numbers for each set up like this, each link with holonomies and stuff. So it gives you these numbers. And now I want to point out something important here. Because I didn't say this, but when I wrote down this S, there was no choice of metric anywhere. It was naturally a three form you could integrate over the manifold. There's no choice of metrics. Which means, and the same here, there's no choice of metrics here. Which means if you give physical meaning to this by some sort of stationary phase, and however that works, it's supposed to not depend on the actual metric. Which means if you try to isotope your loop just a little bit, it's not supposed to change. So it only depends on the loops, the loop equivalence class, the link equivalence class together with these representations. And what then can happen is, and this sounds very discontinuous to me when I hear about it, is that when it passes through itself, I mean, if you don't think in terms of it's supposed to be metric invariant, then passing through itself, it looks like you're doing something continuous. Why shouldn't this just stay the same? But it actually changes. That's the point. When it passes through itself, this thing will change. So if you do some sort of move, it's going to change. Even though, I mean, if you just write an integral and you say everything is continuous in this link, why should it matter? But it does in this interpretation. Okay, so how does one incorporate this into the cobordism picture I was talking about? Well, the best way, I think, is Witten's way, or maybe Seiberg can...
More
More
Seiberg.
More Seiberg. Have this, so you have your manifold M, you have your link inside of it. Maybe it's a loop, I don't know. Not. And then if you cut somewhere at a surface and you want to calculate, you should of course put in points on your surfaces marked with the same type of representations as these links were. So the objects of this cobordism category are now surfaces, but with points marked with representation, marked points with representations. And in principle, I kind of want to say that they should be oriented points, because I didn't say that this is an oriented link. If not, the holonomy actually is only defined up to sine, right, the trace of this. So I want oriented link. Now, this means I kind of want the points oriented as well, because it's supposed to be an oriented cobordism. But you can trade this for taking the conjugate representation, I think. So what you would say is, instead of just saying oriented point with representations, you can just say points with representation. But then if you fill something out, if you have a cobordism that somehow fills between these 2 points, a component of a path, then you want that R1 is the opposite oriented representations to R2. So this is, yeah. So instead of talking about oriented points, we just do this. Now, this is where I get confused a lot when we get to what is this then associated to some sort of, what is C associated to some surface with marked points and representations. And this is supposed to be something like the space of flat connection, which is represented by these holomorphic vector bundles, sections in holomorphic vector bundles. But then you have some sort of holonomy condition I don't understand. Because there was the question whether or not it was the meridian or around the actual link. I mean, I could understand that if it were something like the meridian like this, you would just put the same holonomy condition here. But now, from this point of view of the surface, if you have holonomy going this way around, what does it say about this point when we want the flat connection to be flat? I mean, that's not clear at all to me.
Presumably it will only even work if you have contragradient or whatever opposite representations on R1 and R2, otherwise like it's not
So
even
Jan said
tensor product.
So Jan said Fourier transform. Look at the dual characters and put in characters to.
Yeah, so like dual representation. Yeah.
Okay. Yeah, I don't.
Tensor.
I don't understand,
okay, well,
but it's something like that. In any case, I mean, there is a way of associating these things to surfaces. Oh, I didn't say all of these surface Hilbert spaces are called conformal blocks, if you want to look it up. So, conformal blocks. So the Hilbert spaces as boundaries are conformal blocks, and they're related to conformal field theory on this on the surfaces, actually. So this was a weird insight that topological field theory in 3 dimension localizes to conformal field theory on surfaces, which, yeah. Okay, so now the way I've set all of this up, I've only said that there are some formal properties for these integration, and they're sort of deriving some formal properties for these things, and Witten writes.
Before you erase at board,
Yeah.
is there any compatibility between the representations that you choose?
Not at this point, but I should say that when you then take this surface thing here, the flat connections get some sort of compatibility in the space of the flat. So that the flat connections you allow, at least the sections and bundles you allow, has to sum up to 0 around these, in some sense.
Can you be a bit more detailed here?
I'm already
Okay.
1 minute past the 50-minute limit. I was but I think the official thing is maybe 10 minutes over. I can continue a little bit.
Given 50
But there's
minutes,
other
so
stuff
that
I
the
want to
talk
say
will
as
be
well.
1
So and I can't. I mean, writing down these conformal blocks for me takes a very long time if I should do anything like this. So I'm not going to do that. I'm just saying there is something like this you can look up if you want to, and it has to do with flat connection on this thing that satisfies some condition around these guys, but not.
So is there any, like, you have this link or whatever, right? You can usually like braid it. You can actually consider it as a, I don't know, concatenation of small pieces. Like
Yes, but that's what I'm getting to.
Okay.
That's why I started with the
I
formal
see.
properties of QFT
Yeah.
and stuff like that,
So
and now
there
we're
is
getting to
understanding
Skein
of
relations.
conformal blocks in this.
So, and that's the main point of all of this, of putting it together. So
That's right.
that's the point. I want to say that the formal, so it was proved that these things satisfy like this formal property of a topological quantum field theory, even with these decorations and everything. So what you can do is, to calculate these, you can cut up and see what happens. And this is sort of one of the main points is that if you look at the base case of S2 with 4 marked points, and if you color all of the link, so link colored, this is called the coloring, I think, with defining representation of, let's do UN, so the group G is UN, all of the components of the link are colored by the defining representation, and now we look at the base case of S2, and you have something that looks like 4 marked points where you have the refining representation, which I'm calling R. Then you have R, and R bar, and R bar on S2. This is very important because there's like several ways you can do this, but 3 important ways gives you the Skein relation because you can do this. Then you can, of course, do this. And you can do the other one. Now, it happens to be that when you write down these conformal blocks, especially for S2 with 4 marked points like this, the Hilbert space turns out, so dimension of this Hilbert space of S2 with marked points R bar is 2. And this has to do with representations. One should look at what this has to satisfy, and then you get that it is 2-dimensional. And since I'm running out of time, I'm just going to say that means that these 3 different fillings of this S2 is going to give you 3 vectors in a 2-dimensional vector space, so you're going to get a relation. So you get some sort of relation. And since I'm running out of time, I'm just going to write down what those relations are.
You have at least 7 minutes.
7?
Well, if you go for an hour.
Yeah, 6 minutes. Okay. But I also need to write these. So, I mean, now there's some translation, right? I have an N and a K now. N for U and K. And it depends on these. And we have a description of this in terms of large K, but it still gives you all of them for some reason that Richard identified, and he answered yes to. So I mean, in any case, this is. Yeah, maybe I should just write down. There's this. If you change variables to get lambda, this stuff. So q is this thing. Put q equal to e to the 2 pi. I want anything. I divided by n plus k. So you're not sort of. This is saying that if you write the expansion in terms of 1 divided by n plus k instead of 1 divided by k, you get more natural answers and it looks nicer. So if you put q equal to this and lambda equal to q to the end, so think of this as like some formal change of variables from n and k to q and lambda, then you can interpret what sign relation you see here, and this is coming from really understanding the conformal blocks and how they change under. Yeah, I should say an important piece here is this axiom. If you have a diffeomorphism preserving the structure of the boundary, this is an important piece, right? Because if you do some sort of change somewhere, you can interpret this in many ways as applying some sort of things, some sort of diffeomorphism to the boundary. And that means you can actually use, this axiom is used to then calculate, because you know how diffeomorphism acts on conformal blocks. So you can use this axiom to compute these things and get the sign relation, which tells us that, maybe I should write it like, yeah. So I'm going to write first sign, so give sign relation for Humphrey polynomial, which is q to the n half L plus q minus, yeah. I'm just going to write it, not say it. So if you plug in the representation theory and do calculations on S2 and how things change, and as a little careful, you will get out this sign relation using these axioms for field theory. And this is the sign relation defining the Humphrey polynomial. And I should then say that, well, this means that up to this normalization factor, one can compute, or a physicist can compute, the Humphrey polynomial using these expectation values for these links. So one gets that this expectation value for this guy, which was, well, I was calling it this, CML of link is, no, the expectation value, so I should introduce that, is CML divided by CM. That's the expectation value of this. It's just how it's defined. This is, in this case, lambda to the linking number of L times q n half minus q minus n half divided by q 1 half minus q minus 1 half, the Humphrey polynomial of the link evaluated at dose transformation q lambda. And that's what Witten calculates in his paper out of all these field theories, and use it to, yeah, relate this polynomial with this sort of physically inspired invariant, which is then defined using conformal blocks. I think that is the ending sentence. Okay.
So does there actually exist a mathematical theory with like these conformal blocks and all of that?
Yes.
Like, and does it produce the...
Yes.
Uh-huh. So you can do this actually.
Yes.
Okay.
And references?
Not that I have. I so, in fact, in Aarhus, where I got my degree, they do a lot of this stuff. but I forgot most of it by now. I think I'm not forgotten, but sort of formulas at least, and how to really. I mean, Tobias also often talks about these things, but I mean, this level of details I just gave you, you won't. I mean, if you don't go look at all the details, it's sort of going to be somewhat mysterious, and yeah, I don't know.
There's a book by Bueno.
Actually, book. Now you say it. There is something I like that is this book about from Turayev and Mr. Chicken, who uses tangles and braided tensor categories to define these things. And instead of putting in representations of the actual group and some sort of dual, they're using quantum representation categories. And that gives an explicit way of looking what these conformal blocks are for the surfaces. So I would recommend, that's my preferred reference, Mr. Chicken Turayev's book on tangles and braided tensor categories. Actually, yes.
With this type of approach, is there any simple way to interpret? And then, so you have this polynomial, it's a link invariant.
Yes.
Right, is there any way to see why it's a link invariant?
Well, I mean, the physicist would say we just wrote an integral for it that can be regularized or whatever the word is, or renormalized, but maybe both, I don't know.
Well, it doesn't depend. We average out everything it depends on. So it cannot depend on anything except
What?
I mean, from point of, if you believe all these physics, then
Yeah.
there is no dependence on anything else.
Well, I mean, yeah, but yeah, if you believe the physics, but then there's still this regularization procedure where you need to pick the framing to compensate for this anomaly.
Yeah, no, of course.
But yeah.
But what you do is you figure out what happens on the framing change.
Yeah. And then and that's another point. That's it's easy to see what happens when you change the framing, which means you can also think of this as an invariant of oriented stuff. That's another point as well. Yeah.
Can you similarly define color conflict boundedness?
So I was trying to look up colored and some sort of skein relation for colored, but I mean, as I understand it, the color.
There is no skein relation.
No, yeah.
There is no. Okay, that's probably why I didn't find it. So.
Colored conflict is what you did, but you
Yeah.
use the end symmetric.
I mean, here I restricted the representation. That gave the Humphrey polynomial. But if I don't restrict the representation, this thing is just the color Humphrey thing.
But what you normally call the color Humphrey is the one which has symmetric representation.
Yeah.
Oh, for some n?
Well, the ones that are interesting to us are the symmetric.
So you only look at some of the representations, yeah. But you can still put
the first one. This is the one which just traces in the standard in the one box representation, right? In terms of Young diagram. And then the two boxes and the second color and three.
Yeah. Okay. But isn't that all the representations?
No, this is symmetric.
No. I have all these kind of Young
I don't know representations.
Yeah.
Sorry. Okay. Okay.
But why is there no skein relation? Like the same reasoning with like you can cut and paste doesn't work or something? Or?
So there is one thing I didn't mention here, is that if you want to compute, so really this is also a three-manifold invariant, right? But if you want to compute it for three-manifold invariants, it's also nice to upgrade to this picture of links, because you can relate it to surgery along the links. But somehow when you do a surgery, you have to color it with all possible representations and get some numbers going, and it's sort of a mess, but you sort of use other representation. And I mean, here, first of all, if you have two different representations on these two things, this doesn't make sense, this middle step. That's maybe the simple answer why there's no
short
skein.
I mean, the Hilbert space depends on the representation.
Yeah.
So it's no longer a two-dimensional equation.
Yeah, also that, but I mean, you could still have relations. I mean.
Oh, but you don't have to if there is more dimensions.
Yeah.
Cabling, linking, whatever, cabling, color, and formula. So there's a lot of skein relation. You have to do end. You have to use end cable.
Yeah. Okay.
So, Tobias, you were saying that you can remove the dependency on the framing.
By understanding how it depends on the framing.
Yeah.
Okay. Dividing it up.
But you can also have a framing dependent invariant without this?
It is originally. It is.
Yeah, does it give anything about four manifolds?
So, as I learned from Jan during last break, this Chern-Simons theory on a three-manifold is basically the Donaldson instant well, it's related to the Donaldson instance and fluid homology stuff. Yeah, maybe, yeah, it's related to that, so I think people have already thought about that.
And is it something like very naively take a framed link and look at the format what it represents and hope for the best?
But there is a surgery formula for this. That's how another way of doing this transaminase theory.
But that surgery formula is for 3 manifolds.
Yeah. For 3 manifolds.
But there's also then, I mean, you have to upgrade, but then I don't know what happens when you then go to 4.
Okay.
Any more questions? If not, we start again at 11:40 and let's think time.